Hello, everybody, and welcome to Quantum with Shantum. This episode is 1 plus 0. 2. Did I forget how to count? Well, let's learn how to count. Today, we're going to learn how to count, okay? How does one count? How does one count? For example, how many ways can I arrange 6 different objects in a row, for example? How can I count the number of ways of arranging 6 different objects? And I'm going to make them as different as possible because I'm going to want to talk about 6 distinguishable objects, okay? They look different. Distinguishable objects. And say I'm placing them in a row, okay? They've got these spots here that they can be placed. And let's see, for my first spot, I've got how many choices? Well, I've got 6 distinguishable objects, so I've got 6 choices. For the second spot, I've already used one up, so I only have 5 choices. Likewise, in the third spot, I've already used 2 of my objects, so I've got 4 choices and so on, 3, 2, and 1. But how do I count? How do I count the number of ways of arranging all these different possibilities? Well, it's going to be W is what we're going to call the number of ways of arranging n objects, okay? The number of ways of arranging 6 objects is going to be equal to 6 times 5, okay, multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1. All right, this is how we're going to count the number of ways of arranging 6 distinguishable objects. Now, there's a formulation in mathematics that makes this representation easier to write. 6 times 5 times 4 times all the way to 1 can also be written as 6 factorial, okay? Where the factorial is this exclamation mark sign. So let's define the factorial here. Factorial here, let me define it for positive integers. This is how I would write positive integers, meaning 1 and so on. Factorial is defined as n factorial equal to n times n minus 1 times, like we did with 6 times 5 times 4, going all the way, n minus 2, n minus 3, going all the way to 1. All right, that would be the case where n minus 1 would be 1. All right, and so what is n factorial in terms of counting? Well, n factorial is the number of ways of arranging 6 distinguishable objects, okay? Not 6, n distinguishable objects, okay? That n can be replaced by any number there. Any number which is a positive integer. Now, that is how we count the number of ways of arranging n different objects. But what if I have within those n objects, okay? Within those n objects, so I've got n total for sure, but within those n objects, there are indistinguishable. In other words, indistinguishable. In other words, they look the same, okay? What if I have n total objects out of which r of them look the same? How do I modify my counting now? Well, I'm always going to start by saying the number of total ways of arranging n objects is what? N factorial. They're n total objects. But every time I do my counting, I'm going to count these r indistinguishable objects as well r times, or r factorial times. All right, I would be overcounting that. And so therefore, to account for overcounting, what I do is, well, to account for counting, I multiplied. So to account for overcounting, I divide by r factorial. Okay, so correct for overcounting, correct for overcounting the indistinguishable, or in other words, the same looking objects. Correct for overcounting by dividing by r factorial. Awesome. That's great. Let's do a quick example. Let's think about n particles where, forget about it. Let's take a peek into Mariel's closet, okay? And we find there 11 dresses. All right, we find there 11 dresses where 3 of them are red, I guess, green. 3 of them are green. 2 of them are red. 4 yellow. Okay. There's 1 purple. There's 1 white. What does that make? 5 plus 4, 9 plus 2, 11. All right. So we've got 11 dresses where 3 of them are green. In other words, 3 of them are identical in the way they appear to be green. 2 of them are indistinguishable as well. 4 of them are indistinguishable as well. How many ways can I arrange 11 dresses? Well, as always, I'm going to say there are 11 factorial ways of arranging 11 things, but I would be overcounting for the indistinguishable ones. So I need to correct for that overcounting by dividing by that many factorial. So I've got 3 factorial because of the 3 green multiplied by 2 factorial. But while we're writing factorial, we become fancy and don't write the multiplied by. There's 2 red that I'm accounting for the overcounting for. 4 factorial because of the yellow. 1 factorial, which is trivial, but we'll still write it out for completion. And the other one is white. Then there's also 1 of them. I would be overcounting by 1, basically trivial, meaning it doesn't change our expression because it is 1 factorial. I'm dividing by 1. So there you go. This is the number of ways you can arrange 11 dresses, where 3 of them are green, 2 of them are red, and so on. All right. And this ends up being, I think I calculated here, 138,600 different ways you can do this. Awesome. Great. Now, let's define a specific situation. All right. This situation, this condition, we're going to call the binomial condition, and we're going to see why in a second. Binomial means I've got 2 nomials. I've got 2 stuff. Okay. So in this binomial condition, I'm thinking of stuff like a quantum state being in an up spin state, or a down spin state. Okay. I'm thinking of my coin being either heads or tails. All right. Basically 2 categories where there is a category 1. And if I'm not in category 1, I've got to be in category 2. Okay, that's the binomial condition. If I'm not heads, I'm tails. All right. Now, in this condition, let's see the general expression where we have n total stuff. All right, n total entries, n total coins you begin with, n total particles, or n total stuff. All right, you've got n total stuff, out of which there are r repetitions of category 1. In other words, I'm saying this many electrons are spin up, or this many coins turned out to be heads, are repetitions of category 1. But what does that mean? If that many, if r out of n turned out to be heads, that means the rest of them were tails. So I've also have repetitions in that n minus r repetitions. I've got n minus r repetitions of category 2. So how do I write the number of ways of arranging this n total different stuff, this n system? Well, it's going to be, since there's n total possibilities, it's going to be n factorial, right? But because I'm overcounting by the repetitions, I'm going to have r factorial because there are repetitions of category 1, but also n minus r repetitions. So this entire n minus r gets the factorial, n minus r repetitions of category 2. All right. So this is how I would represent the W4, the total number of ways of arranging n stuff with r repetitions in a binomial category. Okay, in a binomial condition. And this is so special that we're going to specify a different representation of writing this down. All right, this W in the binomial category, where there's n total and r repetitions and n minus r repetitions are the other category, this is going to get its own representation. Okay, but before that, let's do a quick example here. Let's say there are 10 coins. Let's say there are 10 coins, and you're wondering, you just shuffle those 10 coins around, and you're wondering how many ways are there for those 10 coins to be arranged in this configuration. 3 of them are heads, meaning the rest of them, 7 of them, are tails. Okay, how many ways can you end up with this configuration if you have 10 coins? Well, that is equal to W, the number of ways of arranging 10 things, which that many repetitions, is 10 factorial over 3 factorial times 7 factorial. Okay, perfect. Perfect. Now, this W, we said, this binomial W, let me be specific, this W coming from the binomial condition, this binomial W, which we defined as n factorial, number of repetitions R, number of repetitions of the other category n minus R. This is gonna, in combinatorics, is given another representation called n choose R, written like this, okay, with these big parentheses around it. It's not a vector, it's not a matrix, it's just written like that, okay? N choose R. How do we say this? It is n choose R. All right, and this, as is evidenced by the fact that of why we call this n choose R, is this can also be this can also be thought of as the number of ways of choosing R stuff, the number of ways of choosing R stuff from n total stuff. Okay, that's the same as saying number of ways of arranging n total stuff with R repetitions and n minus R further repetitions. Okay, so that's just n choose R, but it happens to be the case that these numerical quantities of n choose R, right? These numerical quantities, which can be calculated like so, these numerical quantities actually form the Pascal's triangle. How crazy is that? Let's verify that. So if I have the 0th line in the Pascal's triangle, it's 0 choose 0. So it's just 1. Great. If it's 1, if n equals 1 now, it's 1 choose 0 or 1 choose 1. So it's 1 choose 0 is 1, 1 choose 1 is also 1. How am I figuring it out, by the way? I'm plugging it into this formula right here, n factorial over r factorial n minus r factorial. Now n equals 2. I've got 3 options: 2 choose 0, 2 choose 1, and 2 choose 2. 2 choose 0 is 1. 2 choose 2 is 2 factorial over 1 factor 1 factor, that gives me 2. And 2 choose 2 is 1 again. This definitely looks like the Pascal's triangle, doesn't it? Now let's quickly do for n equals 3, and then we'll be done. N equals 3 is going to be 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. 3 choose 0 is going to be 1. 3 choose 1 is going to be 3 factorial over 1 factorial, 2 factorial. 2 factorials cancel, you get the 3. 3 choose 2, same deal. And 3 choose 3, 3 factorials cancel, so it's 1. All right, so these can also be derived from the Pascal's triangle. Beautiful. All right, what's more? What's more is that these n choose k's, these n choose r's, sorry, these n choose r's are also, and that means the Pascal triangle representation is also, n choose r's are also coefficients. Coefficients to what? Coefficients to the binomial expansion. All right, I'm going to talk about this in just a second. Coefficients to the binomial expansion. And what binomial am I expanding? It's the binomial called a plus b raised to the n. Okay, so these n choose r's apparently, which are also the terms in the Pascal triangle, are also coefficients to the binomial expansion of a plus b to the n. What do I mean? I mean, when you expand something called a plus b, which is a binomial. When you expand this binomial raised to the n, this expansion yields, for example, let's do for n equals 2, we know if it's a plus b squared, what is it going to be? A squared plus 2ab plus b squared. And that's immediately clear from here. A squared, the coefficient of a squared is 1, plus 2ab, the coefficient of ab is 2, plus b squared, coefficient is 1. All right. What is a plus b cubed? Well, it is x cubed, as in a cubed, plus 3a squared b, plus 3ab squared plus b cubed. All right, so it nicely works out that it is true that these n choose r's are also coefficients to the binomial expansion a plus b to the n. Let me write that out explicitly. This is actually, because this is a sum, we're going to have a sum r equals 0 to n of what? N choose r, exactly, n choose r, but a is going to get the exponent of n minus r, right? Because the first term we want to be a to the n, right? A to the n, and the first term is going to be r0. So it's a to the n. And then r, not r, sorry, b to the r, right? A to the n minus r, b to the r. All right, let's expand some terms for this. This first term is going to be n choose 0. N choose 0, a to the n minus 0 is n, b to the 0, right? B to the 0 is also 1, plus n choose 1, a n minus 1, b, and so on. All right, all the way till n choose n, a to the n minus n will now be 0, b to the n. Awesome. So what do we have here? We know how to expand a plus b to the n. Great, great, that's great. Let's apply it real quick. Let's apply it real quick to a very important expansion, and we're going to see why it's important very soon. A very important expansion called 1 plus x to the n. All right. What does 1 plus x to the n expand to? Well, I'm going to use the same thing. Well, it's n choose 0. N choose 0 is always 1, right? N choose 0 is always 1. So the first term is 1 times a to the n. Well, a here is 1 in my case, right? A plus b, same as 1 plus x here. A to the n is 1 because 1 to the anything is 1. So I don't need to bother about this a term anymore because it's always going to be 1. So I'm only ever concerned about the b term, which is the x term in this situation. Okay, so my first term is just going to be 1 times 1 times 1. So it's just 1, right? My second term is n choose 1. So how am I going to write this? I'm going to write this as n factorial over n minus 1 factorial times 1 factorial, right? Let me skip out on the 1 factorial. Actually, let me write it out just for completion. And then a to the n minus 1, like we said, it's 1 to the anything, it's 1. We're not going to worry about that. And then we've got b here. We've got b, which is the same as x. X plus, let's write out 2 more terms, okay? Plus, what is this going to be now? N choose 2, right? N choose 0, n choose 1, n choose 2, all the way to n choose n. So n choose 2, how do I write n choose 2? Well, it's n factorial over n minus 2 factorial, and 1 to the anything is 1. And then I'm going to talk about x squared. Okay, perfect, perfect. What's the other term? Well, we could stop here, but let's keep going actually. N factorial over n minus 1 factorial. I mean n minus 3 factorial, x cubed. Okay, all right. Now let's go. All right, so this is just the representation of 1 plus x to the n. This is how you would write, and then plus it keeps going on all the way to n choose n, b to the n. So it goes all the way till x to the n. All right, some coefficient times x to the n. All right, so now let's move on to the point where Newton came into this um, Newton came into the scene. Okay, so enter Newton, and we've always been trashing Newton in terms of, you know, his theories of gravity isn't really a theory of gravity, like he's only approximate ever, and so on. We always trash Newton like that. But today we're absolutely going to praise homie because he he discovered an ingenious way of approximating the numerical representations of certain numbers, all right, like square root of 3, for example, or pi, for example. Okay, so we'll check that out, how Newton was able to do it. Remember how we said the factorial is defined for positive integers, and in the binomial condition, how we just never talked about these n's being anything other than positive integers, right? We just started out imagining these are positive integers, but Newton said, let me take this up one more notch, all right? And then Newton applied it to the condition where n equals -1, all right? And this is fun. This is so much fun that this is actually the extra credit problem where you ought to prove what that this formula also works for n equals -1, all right? And he also not only applied it to n equals -1 and got fascinating results, but he also applied it to fractions. Are you kidding me? This expression right here, the binomial expression right here, he applied this to fractions. In other words, we're talking about fractions instead of these factorials here, as in fractions of factorials of fractions. Okay, so that seems counterintuitive and totally not defined, but he was able to show that it gives absolutely real results. So he applied to the case, for example, n equals half. All right, what do we get when we apply to n equals half? Well, we could go to a plus b to the half and do the analogous expression, or we could use this. Let's entertain this form of that example. Let's entertain the 1 plus x to the n form of that example. Okay, let's see 1 plus x to the n where n is half. If n is half, I can replace the n by half here. And what is this going to be? Well, first of all, our expression was 1, so the first term is absolutely just 1, plus. It was n factorial over n minus 1 factorial. All right, how can I write this better? N factorial can also be written as n times n minus 1 factorial. Isn't that true? 6 factorial is the same as 6 times 5 factorial, right? N times n minus 1 factorial is the same as saying n factorial. And I've got my n minus 1 factorial in the denominator. And I've got x here, okay? And I've got x. So these n factorials are going to cancel to give me n, all right? And I can use that pattern. I can use that pattern to now generate the further terms, which are going to look like this. It's going to be n times n minus 1 over 2 factorial of x squared, right? Over 2 factorial, right? The n minus 2 factorial is going to cancel when I write n as n times n minus 1 times n minus 2 factorial. And now for the last term, or rather the third term, it's n minus 1, n minus 2 over 3 factorial, x cubed, and so on. All right, awesome. So all I need to do now is plug in this guy, right? Plug in, instead of n, I need to plug in half. All right, but before that, let's see the context real quick. Let's see the context real quick. Or do we want to plug in first? All right, sure, why not? Let's plug in first and then see the context. So if I plug in n equals half, I've got 1 plus half x, right? And I've written this down nicely here. Half times half minus 1 over 2 factorial x squared plus half, right? I'm just plugging it in, half minus 1, half minus 2 over 3 factorial x cubed, and so on. All right, this is what it looks like. Now, let's take a short interlude and come back to this, okay? And in this interlude, let's entertain our old friend, the unit circle, okay? Let's imagine this curve to be a circle of constant radius, which I'm going to call, because I said unit circle, this is going to have radius equal to 1, okay? I'm going to label my 0. I'm going to label minus 1, all right? And if I want to write an algebraic form of this function, I better label my axes so that I can use these variables. If I call this guy y, this guy x, then the equation of this circle with constant radius 1 is x squared plus y squared equals 1, okay? Which can also be written as x squared. No, I don't want x to be my subject. I want y to be my subject. This can also be written as y squared equals 1 minus x squared. Sure. This can also be written as, well, y equals plus minus square root of 1 minus x squared. Okay. But if I were to focus just on the top half of the circle, meaning just on the positive values of y, okay, just on the top half of the circle, which I'm going to highlight with this red curve here, just the top half of the circle, just the positive part of the y-axis, then I can say y equals square root of 1 minus x squared. Okay, and this I can also write as, guess what, 1 minus x squared to the half. Okay, so this is starting to look very much like a binomial approximation problem, okay, where instead of x, remember how we did 1 plus x to the half, instead of x, all we need to do is substitute that x for minus x squared. What would that do? Well, if we substitute x for minus x squared, then we would be talking about the top half of a unit circle. Okay, so let's do that. Let's see what that looks like. We're plugging in the binomial expansion when we do 1 minus x squared to the half. All right, this leads me to this this expression here. Got 1 minus half x squared. All right, and this you can verify on your own. 1 over 8 x to the 4th minus 1/16 x to the 6th minus dot dot dot. All right, it keeps going. Now, how does this help me with anything at all? Right? Why was Newton thinking about this? Well, Newton had also just developed what's called calculus, and using calculus, he was able to find the exact area of the top half of the circle, which he could conveniently distribute into two halves and have this 1/4 into 2 quarters, and conveniently talk about only this 1/4 of a circle. Okay, so what he showed using calculus is that when you integrate this function which goes like so, this function which has what representation? Which has the representation square root of 1 minus x squared, which has the representation 1 minus x squared to the half. When you integrate this function from 0 to 1, what should you get? Well, that is the area under the curve, right? So that is the area of a quarter circle, quarter of a unit circle. What's the area of a unit circle? Well, it's pi r squared, where r is 1, so it's pi. And so quarter of a circle is pi over 4. Quarter of a circle is pi over 4. All right? But he also found a way to represent what's inside here, right? Let me integrate this with respect to x, by the way. When I do this integral now, it's going to be pi over 4. Awesome. But he also found another way to express the integrand here, which is 1 minus x squared to the half, which is this infinite series expansion, right? This is an infinite series expansion. And because he could equate these two sides, he also integrated those two sides. And now 1 minus half x squared minus half x to the 4th minus 116 x to the 6th, and so on, right? And now if I integrate this polynomial expression with respect to x, I should get what? Exactly pi over 4. All right? So now, what does this imply? This implies pi equals 4 times this entire integral, right? 4 times this entire integral, which looks like what? Well, it looks like 1 integrates to x minus half times x cubed over 3, right? Minus 1/8 times x to the 5 over 5 is what I get after I integrate x to the 4th, minus 1 to the 16th times 1 over 16th times x to the 7 over 7, right? And these plugged in at 1, 0. Since these are polynomial functions, plugging in 0 is just going to give 0. So what does that mean? Now I have, and this is dot, 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 by the way, because it's an infinite series. Now, what does that mean? This means I have a representation, a numerical representation of pi to arbitrary precision. How cool is that? I can go all the way up to however many decimal places I want by keep on adding more and more terms in my expansion of this function. Okay, if I keep on adding more terms, I get more and more digits in the expansion of pi. All right. Whew. Wow, that was beautiful. How precise do you want your pi to be? Let me know in the comment section. Okay. And for today, this is going to be it. Thank you so much. Bye-bye.